So we're finally moving away from the trigonometry unit today. We're going to start talking about exponential functions. Let's get going. So we're starting chapter 7 today, covers exponential functions. Chapter 7 and chapter 8 are going to merge together. They cover two things that are actually very similar in concept, and there's no point in really separating the two. So you're hardly going to notice the difference between chapter 7 and chapter 8. Anyway, so the focus for today is going to be on identifying exponential functions. We're going to talk about how to graph an exponential function. If I gave you an equation, we'll talk about how to identify whether an exponential function is a growth function or a decay function. That'll make more sense in a moment. And we'll create an equation for an exponential function given the graph. So we're just going to cover the basics of exponential functions today. Here we go. So first things first, you're probably wondering, what on earth is an exponential function? Hey, maybe you already know. Who knows, right? So an exponential function is a function where the independent, or in other words, the manipulated variable, x, is in the exponent, right? So the variable itself is not down in the base, it's up in the exponent. So there are many uses for exponential functions, such as population growth, a physics principle called half-life, as well as like an accounting kind of principle called compound interest. Now, the general form of an exponential function is y is equal to a times b to the power of x. And what's important to understand here is b is the base of your power, and it's being taken to a power of x, right? A is just your coefficient out in front. We'll talk about what all of this does in just a minute, of course, but a, of course, is generally your starting value, and b is your growth decay factor. You know, again, that may or may not make sense right now. We'll see it in a little bit more detail in a little bit here. Now, just out of general interest here, I put the formula for compound interest, which again is like basically the amount of money you're making by putting it into an interest account in a bank. Like you're putting your money into an interest account in a bank, and it's going to be earning interest on it and then compounding over time, right? This is a very advanced type of exponential function. Well, I wouldn't say very advanced, but it's just a more structured form. But the bottom line on this is your variable is your time, which is usually measured in years, and that's your exponent. Yes, you can see there's an r and an n and a p over here as well, but those aren't really variables. They're things you'd actually be plugging in. So for example, your principal is what you're actually putting into your account in the first place. So let's say you threw $5,000 into an account, p would be 5,000, and then you have 1 plus r divided by n, so it's your interest rate divided by the number of times interest is compounded per year, right? And that n also shows up in the exponent as well, but again, that would be given in the problem itself. All right, I'm going to stop rambling. First thing here, circle the functions that qualify as exponential functions. This might seem like baby food, but you know what? We're going to do it anyway because it's important to understand what is and what is not an exponential function. I'm going to run through this. I'm just going to do it like top left and then work to the right and then do the second row. This very first one here, y is equal to 5 to the power of x. X is the exponent. I see no reason why that's not an exponential function, so I'll circle it. This one, however, y is equal to x to the power of 5. That actually is not an exponential function because remember the exponent needs to be your variable. This one here, 1/5 to the power of x. Your base can be a fraction. It really doesn't matter. So you know what? That is an exponential function. This one, though, no, it's not because your variable is your base. This next one, 2 times 5 to the power of negative x. Negative x is your exponent, right? That's your variable. So that one works just fine. Negative 5 to the power of x. Yeah, that works too. Negative 5 in brackets to the power of x. Yeah, that works. Just a reminder what the difference is between these two. In this one right here, what you're doing is you're doing 5 to the power of x, and then you're timesing it by a negative 1. Whereas with this one, what you're multiplying by each time is negative 5. So you're going negative 5 times by itself x number of times, right? That's basically the difference there. It's subtle, but it's important to talk about nonetheless. Now for this one, 0.5 to the power of x, again, x is an exponent. We're good there. This next one, y is equal to e to the power of x. E is actually a pretty special number. We'll talk about that more in chapter 8. It'll become much more useful. I can never remember exactly what e is equal to. It's kind of like pi where it's an irrational number. I just threw it in my calculator right now. E is approximately equal to about 2.718 and a bunch of other stuff, right? So again, it's just an irrational number. It goes on forever and never, and it has some very important purposes that we will again investigate more in chapter 8. But again, because it's e to the power of x, x is your variable, that's up in the exponent, we're good. Same with this one, pi to the power of x. Pi is just a number, right? It's just like anything else. It's an irrational number, so it still works, okay? Hopefully that set things straight. Hopefully that wasn't tough or anything like that, but if it is, let me know. All right, here we go. We're going to do a real example here now. Sketch the graph of y is equal to 2 to the power of x and complete the following information. First things first, when I make exponential graphs, I try to make a table, right? You can put as many data points in the table as you wish. I'm only going to put 5 points in, as you can see right on this table here on the far right. Let's just throw these numbers in. So when x is -2, we're doing 2 to the power of -2. Now a negative exponent is kind of weird. I'll actually write it just kind of over here. 2 to the power of -2. Negative exponents are weird in that what that negative really does is it does a reciprocal, so it turns it into 1/2 to the power of a positive exponent. So it's like saying 1/2 to the power of +2, right? So in other words, 1/4, or we could write that as a decimal if we wanted to, 0.25. Now, same with 2 to the power of -1. 2 to the power of -1 is 1/2 to the power of 1, or in other words, just 1/2, which is 0.5. 2 to the power of 0, hopefully you remember any number to the power of 0 is always equal to 1. The only exception would be is if I had this as y is equal to -2 to the power of 0. Well, then 2 to the power of 0 would be 1, and you'd have negative times 1, so -1, right? That'd be the only exception. If you did this, however, y is equal to -2 to the power of 0, where -2 is what you're actually taking to the power of 0, that would be +1. Okay, so just important to understand the difference. Brackets are really important sometimes. All right, next up, x is 1. Well, 2 to the power of 1, that's pretty easy. That's just 2. And then 2 to the power of 2, that's not bad either. That's just 4. So now we have a pretty good idea of what this is going to start looking like. Hopefully, we can start plotting these points on our graph. Again, I'll just use each one of these little squares as just 1, both in my x and my y. So I'll be lazy this time. In other words, I'm not going to label all of it just for the sake of time. I'll start at -2. When x is -2, y is 0.25, so it's about right there. When x is -1, y is 0.5, so it's about right there. When x is 0, y is 1. When x is 1, y is 2. And then when x is 2, y is 4. So it might be kind of clear what this is looking like right now. It's not going to be a straight line. It's definitely going to have a curve to it. If we wanted to go a little further, we could say, okay, x is 3, so 2 to the power of 3 is actually 8. So I can plug that one in just for really good measure here, 5, 6, 7, 8. That makes it a lot more clear what this is going to look like. If you're wondering what it's going to look like down here, well, let's try something crazy. Let's try like -10. If I did x is -10, 2 to the power of -10, I'm going to have to put that in my calculator. 2 to the power of -10 is a really, really, really small number. Putting it as a fraction, even putting it as a fraction, my calculator doesn't really want to do it. Okay, I'll do it this way. It's going to be 1/1024, so like 1,000th basically, and that again is when x is -10. So you're like just above the line right here, just barely, right? Hopefully what you can imagine is if we made x go all the way to -infinity, you're going to be doing 1 divided by 2 to the power of infinity, so 1 chopped into virtually an infinite number of pieces. It's still not going to be 0, but it's going to be pretty darn close, okay? That's going to be important. Anyway, if I'm going to graph this right now, I'll just do my best. This is going to be next to impossible with this trackpad I've got. We're going to follow the x-axis here, and then we're finally going to like go whoop, and up we go. Just doing it one little segment at a time. This is way harder than it probably looks. This trackpad thing is just a nightmare. Anyway, there we go. That's going to be what your exponential function looks like. We're good to go on that. Now, let's get to the real meat and potatoes of this. We're going to look at the domain, range, x-intercept, y-intercept, and asymptotes. Domain, again, is just your possible x values. Ask yourself this: is there any x value you could throw in here that would not work? Well, actually, there isn't, right? So in other words, your domain is going to be x as an element of all real numbers. You can plug in whatever x you want into this. It doesn't really matter, right? You're not going to have like a divide by 0 or anything like that. You're totally fine. Now, as for your range, like I mentioned before, when x goes closer to -infinity, your y value is going to get pretty darn close to 0. But you have to realize your y value will never actually hit 0 with these exponential functions. So we can say that y is always going to be strictly greater than, not greater than or equal to, strictly greater than 0, okay? As x goes to positive infinity, we're looking at 2 to the power of infinity. That's going to take our y all the way up to positive infinity. So we'll just keep on going, right? So there's no problem with our range on that one. Next one, x-intercept. Where do we cross our x-axis? Well, that's a trick question. We don't cross our x-axis. As I even said, we're going to get really close to it as we go closer to negative infinity, but there is no x-intercept. because you're never actually going to touch that x-axis. You're going to get really close, but you're not actually going to get there. Now, the next one here, Y-intercept, this one's kind of interesting. Y-intercept is where we're crossing our y-axis. You can see based on the thing we drew here that it's going to happen at y is equal to 1, right? So when y is 1, we're crossing our y-axis. Y-axis, of course, always occurs at x is 0, so that's how you could always find that. To find your y-intercept, just plug in where x is equal to 0, and you've got it. You'll see something kind of interesting with that as we do some other examples, but again, we'll get there when we get there. Now, as for asymptotes, it's been a long time since we've talked about asymptotes. An asymptote is basically just a vertical or a horizontal line that your graph cannot touch. Now, you might be looking at this and start thinking, oh, I wonder if there's going to be like a vertical asymptote somewhere around here. Well, there actually isn't going to be a vertical asymptote. There's going to be nowhere on here that you can't touch vertically, or like a vertical line somewhere along your x-axis or whatever that you wouldn't be able to touch. So no, there won't be a vertical asymptote, but there is going to be a horizontal asymptote. Remember, you're not going to be able to touch your x-axis, and because of that, we can say that our asymptote, for horizontal at least, so horizontal, is going to be the line y equals 0. Now remember, y equals 0 is a horizontal line. Don't get confused with the fact that that's your x-axis. It is where y is equal to 0. For example, if I said y is equal to 4, if y was always equal to 4, you'd have a horizontal line up here at y is equal to 4, right? So in other words, just be careful with that. We do have a horizontal asymptote, and with these exponential functions, that is the type of asymptote we're going to find. All right, we're going to do another few examples here. We're going to fly through these a lot quicker. I just kind of rambled there because that was the first one. Sketch the graph of y is equal to 5 to the power of x and complete the following information. All right, so let's start with 5 to the power of negative 2. That, in other words, I'll just do it over here again. 5 to the power of negative 2 is equal to 1 over 5 to the power of 2. Well, 5 to the power of 2 is 25. 1 out of 25, I think I know what it is, but I'm just checking on my calculator. Yep, it's what I thought it was, 0.04. That's what we've got there. Next one, 5 to the power of negative 1 is 1 over 5. Well, 1 over 5 is 0.2. Now, the next one, 5 to the power of 0, like anything else, is going to be 1. 5 to the power of 1 is going to be 5, and 5 to the power of 2 is 25. So let's start plotting this as best we can. Most of these numbers are going to fit on our graph, but one of these numbers in particular is not, and that's okay. So when we have x is negative 2, we're at 0.04. So really, really, really close to our x-axis there. When x is negative 1, we're at 0.2, which is maybe about right there. That might even be a bit of an exaggeration. When x is equal to 0, y is 1. So far, it looks pretty much exactly the same as the other one, although these points are different. They're just so small and so close to 0 that they might as well not be different. However, when we see x is 1, y is going to equal 5. That is a lot steeper than what we've seen before. And then when x is 2, y is 25. It's way off the chart. Can't do anything about it. Just like before, we're going to be hugging our x-axis here. Again, I'm going to try my best to get this. It's really, really tough to get a line going on this. And then, oh, see, even there, I kind of screwed up. We don't want to cross that line too early. There we go. That's better. And then that's just going to shoot right upwards, just like that. Awesome. All right, so that's our graph, a very, interesting sketch. Let's compare it with the one on the last slide. Oops, there's our one right now. There's a one on the last slide. Hopefully what you're noticing is there's like a lot more steepness to it or something, right? It slopes up a lot quicker than the other one. It's a lot sharper of a graph than the previous one. But let's check all the basic info on this one. Let's start with the domain. Once again, there's nothing wrong with any x you plug in here, so our domain is once again going to be all real numbers. And our range, once again, is just going to be y is greater than 0, strictly greater than. Important to understand. X-intercept, do we have one here? Nope, no, we don't. We're going to get closer to 0, closer than the other one, but really it doesn't matter because even if you had an exponent to negative infinity, you're still not going to get there. So nope, no x-intercept. As for y-intercept, this is kind of boring. Y-intercept is the exact same as before. Y is equal to 1. We changed the base, but that had nothing to do with the y-intercept. How curious. Next up, asymptote. Once again, we have a horizontal asymptote, and that's going to occur at y is equal to 0. In terms of all this basic information, changing the base of our function did nothing to affect these. All it did was affect the slope of our graph and the points on that graph, but the basic information, domain, range, all that, that didn't change. Very interesting. Think about that, ponder. All right, next one. Sketch the graph of y is equal to 1/2 to the power of x and complete the following information. This one, This one's going to be a little trickier. Let's start with those negative exponents because they're going to be really pesky. 1 over 2 to the power of negative 2. Remember in the other ones I said take the reciprocal of it and then put it to a positive exponent. It actually works the same way with this. Take the reciprocal of your base, so it's going to be 2 over 1 to the power of a positive exponent. Well, that's to the power of 2. Well, 2 over 1, of course, is just 2. 2 to the power of 2 is 4. So we can say 1/2 to the power of negative 2 is actually 4. Interesting. What about this one? 1/2 to the power of negative 1. Well, again, take the reciprocal, 2 over 1 to the power of positive 1. Well, that's just going to be 2. There you go. Cool. What about x is 0? If x is 0, 1/2 to the power of 0, it's just like anything else. It's going to be 1. 1/2 to the power of 1 is going to be 1/2, so I'll write it as a decimal, 0.5. And then 1/2 squared, or in other words, 1/2 to the power of 2 is going to be 1/2 times 1/2, which is 1/4, so 0.25. Let's start plotting this. So when x was negative 2, y was 4. When x was negative 1, y was 2. When x was 0, y was 1. When x was 1, y was 0.5. And when x is 2, y is 0.25, so about right there. If you really want to go crazy with this, you could try an x to the power of negative 3, because we could see like, oh, it's going to be going up here somewhere. We can find exactly where that is. Well, I'll do it kind of just up here. 1/2 to the power of negative 3 would be like saying 2 over 1 to the power of positive 3. Or in other words, 2 to the power of 3, which is 8. Cool. Anyway, so negative 3, 8. There it is, 8, right there. Awesome. So we can just plot it, no problem. That gives us a better picture of what we're doing. It's basically just a flipped around version of what we had before. That's quite interesting. Let's just start connecting these lines as best I can. I'm not doing the best job here, but hopefully you're getting at least the idea. And I'll hug the x-axis here without really actually crossing it. Good to go. Cool. All right, so we'll talk a little bit about what that did in just a moment. But before we get there, let's figure out our domain, range, and all that. Domain, once again, x is an element of the real numbers. Range, once again, y is greater than 0. Our x-intercept, once again, does not exist. Y-intercept, once again, is just y is equal to 1. And our asymptote, yet again, y is equal to 0. And again, I should label that as being horizontal. None of that information changed, even though we drastically changed our base. It's almost like none of this information has anything to do with the base of an exponential function. Interesting. So what I do want to note on this one, though, is like I mentioned before, it's kind of like a flipped around version of the ones we've looked at. That shouldn't be a surprise. The type of flip that this is a horizontal reflection. It's a horizontal reflection. Now, with a horizontal reflection, remember, in function notation, we always said that that was basically like taking a negative and putting it in with your x. So in other words, it's almost as if what we did was we took an original function, f of x, and changed the x to be a negative x. Okay? Bear with me on this one. Imagine if we took, let's say, an original function of y is equal to 2 to the power of x. And if I changed it using this function notation, I could change it to y is equal to 2 to the power of negative x. But by the definition of a negative exponent, that would be like taking the reciprocal of the base, 1 over 2, to the positive exponent. Well, look at that. 1 over 2 to the power of x, which is what this question is looking for, is therefore the horizontal reflection of y is equal to 2 to the power of x, which is the first example that we did, right? Kind of an interesting result out of that. And again, you didn't need to make that connection, but it is kind of a cool connection to make nonetheless. Moving on, next one, sketch the graph of y is equal to 2 times 3 to the power of x and complete the following information. So this one, we're throwing a coefficient out in front. Hopefully that's going to change some of this information. Maybe it will, maybe it won't. Let's find out. Before we do this, maybe remind yourself with the whole function transformation thing we did back in the beginning of this course, what would multiplying the outside of an exponential function by a coefficient, what would that do to the function? What kind of an effect would that have? I want you to think about that. I'm going to run through this. So let's do negative 2, of course. So y is equal to 2 times 3 to the negative 2. Well, 3 to the negative 2 is like 1 over 3 to the 2, so it's like 1 over 9. So in other words, that's 2 over 9. 2 over 9 is 0.22. If we did y is negative 1, we'd be looking at 2 times 3 to the power of negative 1. I'm not going to write it down over there, but that would be 2 times 1/3. 2 times 1/3 is 2/3. 2/3 is 0.66. When we have 0, 3 to the power of 0 is 1, but then we're timesing by 2, so that's going to be 2. No problem. and also quite interesting. Let's see the next one. If x was 1, we'd be doing 2 times 3 to the power 1, so 2 times 3, that's 6. And if x was 2, we'd be doing 2 times 3 to the power 2. 3 to the power 2 is 9. 9 times 2 is 18. Let's plot these numbers in here. X is -2. We got y is 0.22. We have when x is -1, y is 0.66. When x is 0, y is 2. When x is 1, y is 6. And then when x is 2, y is 18. It's off the chart. So in other words, we can graph this now. There we go. And up we go from there. And we're going to lift off from there. Awesome. Okay, let's analyze the results we got. Domain. Did our domain change by putting a coefficient in front of this? Nay, it did not, right? So a range, however, range also didn't change. You know, oftentimes doing this kind of a transformation would affect the range, but didn't in this case because, again, we're kind of anchored with our x-axis there. So we'll say it's y is greater than 0. As for our x-intercept, we still don't have one. As for our y-intercept, this is where things are a little different. Y is now equal to 2. We'll talk about that in a second. Now for our horizontal asymptote, once again, we have y is equal to 0. So I want to talk about this y-intercept because that's the only thing that changed. Hopefully the connection you're making here, with all the other ones, we had a y-intercept of 1, but with this one, now that we add this coefficient out in front, we now have a y-intercept of 2. This coefficient out in front is actually going to be your y-intercept. On one of the very first slides we had today, I said your a value, that's what this is, your thing out in front, is often regarded as being your starting value. And your starting value, of course, is where it is when x is 0. So when you have x is 0 right here, your starting value is that a value. And your starting value, of course, is also your y-intercept. Kind of neat. So to summarize, the general form of an exponential function is y is equal to a times b to the power of x. In terms of a graph, what does a tell us? Well, we just answered that one. A would tell us our starting value, or in other words, maybe more useful to us, it's your y-intercept. But what about our b value? What does that do? Well, in terms of what it's really doing is it's multiplying by b every single time. But in terms of a graph, what really does that mean? Well, if we look back at some of the examples we've done, this one, of course, had a b value of 3, so that's notable. This one was the most notable one, b value of 1/2. Notice the shape. This one, b value of 5, compare it to b value of 2. Basically, what you can say in terms of a graph is it affects the growth rate. So the higher the b value, the faster it's going to grow. Another thing to make note of this is if b is between 0 and 1, kind of like it was when it was 1/2, you'll have what's called a decay function. And a decay function takes this kind of an appearance, because as x is increasing, your value of y is decaying, it's decreasing. If the b value is greater than 1, you'll have the growth function. And a growth function, of course, looks like all the others, where it looked more like that. Okay, so make sure you understand that in terms of a graph, your a value tells you your y-intercept, or in other words, your starting value. And in terms of the graph, your b value is affecting the growth rate. And you have to understand if it was greater than 1, you have a growth function. So b greater than 1, it's a growth function. If b is between 0 and 1, however, you have a decay function. All right, this is the last one we're going to do here. Getting a function from a graph. Create an exponential function from this graph. And I even threw in the table of values just to make things a little bit more clear, because it's kind of hard to read this graph. Here's how we can go about this. Remember before, an exponential function needs to have the form y is equal to a times b to the power of x. That's just a very general form, of course. If you wanted to add more transformations in there, you could, like a horizontal reflection or a horizontal shift or all that sort of stuff. But this is just a very general blanket base form of an exponential function. That's all we're going to worry about here. A is your starting value, and b is your growth or decay rate. Hopefully what you can tell, based on the shape of this graph, is that this is going to be a decay function, because it's going downwards. What this tells us is b is going to be some value between 0 and 1. And usually when we do this, b is going to be represented as a fraction. Not always, you could represent it as a decimal if you wanted to, but a fraction is usually the way we go about this. Your a value, however, is your starting value. Your starting value on this is clear not only from the graph, but also from our table. Your starting value here is 4. So based just on that information alone, we can already determine that our function here is going to look something like y is equal to 4 times b to the power of x. Now our job is just to find what that value of b is. Well, the good news is we have other points on our graph that we know. We could throw those points in and then help us solve it. Probably the easiest point to use here would be where x is 1. If you throw in x is 2, you'd have b squared and you'd have to square root both sides, but that's fine as well. I'm just going to use where x was 1. This means we have 4/3 is equal to 4 times b to the power of 1. Now b to the power of 1, of course, is just b, so I can just ignore that 1 altogether. So the next thing we can do is we can just divide both sides by 4 to get b by itself. 4/3 divided by 4, hopefully you know that one, is 1/3. So 1/3 is equal to b. We now have everything we need, right? We're good. So in other words, to finish this question off, I'll just do it up here in the top right-hand corner. Y is equal to 4 times 1/3 to the power of x. That would be your exponential function. You have your a value and you have your b value, and x is up here in the exponent. All right, so we're done for today. What I want you to do now is I want you to do page 342, questions 3 to 8. There's a couple word problems in there. Don't worry, even though we haven't done any word problems in this lesson, you should be just fine. As always, if you have any questions, contact me, and best of luck.